Right, so a quick recap of what we had done in the last lecture. So we started with harmonic oscillators. So I told you the first thing we'll talk about is an oscillator which is undamped, that is there's no friction, so that's more of a recap. So we talked about undamped oscillators, we talked about the solution of the equation that we have for undamped oscillators. So that's a second order ODE without any x dot term in this case. So the solution for that is a wave-like solution, and from the energy side we talked about the potential and kinetic energies. So this is a system under conservative forces only. Okay, till now there is no damping, so there is no loss of energy. So energy remains constant, and we saw that that is indeed the case. Half k square is constant, the total energy. Then we talked about time averaging, just to calculate the time average kinetic and potential energies in an undamped harmonic oscillator. Then I talked to you about a damped harmonic oscillator that is more realistic. So in a damped harmonic oscillator, as the oscillator moves, now this oscillator could be anything, we are just modeling it as an oscillator. So in this case, the friction force will dissipate energy, so the energy will go down with time, and we will want to model this system in the sense to calculate the output or the position as a function of time for this mass in the oscillator. Okay, so the equation has a new term here, that's a friction term, in addition to the restoring force because of the spring, and the friction term again has to be modeled depending on what kind of friction is acting in the system. So in this case we said that we have a friction which is of the viscous type, that is as the velocity increases, the friction increases linearly with velocity, and velocity is nothing but the first derivative of the position. Okay, and this constant B is called the viscosity or the friction constant. So the equation that we have looks the one that we have in the box. So in this case, as compared to the undamped system, we have an extra term now, which is B upon m times x dot. So we will want to solve it now mathematically and analyze the solution and see what is the physical aspect related to that system. So towards the very end, I told you that we can use the complex numbers approach to solve this system. Any questions? I had asked you and you had told me that you have not studied how to solve these kind of equations using complex numbers. Was that right? So we'll want to solve it because that's a very important method used for solving differential equations. Right, so please settle down. So we'll have the constants here, gamma. So we'll call B by m as gamma and K by m as omega naught square. So K by m being omega naught square is something we have been using for the undamped systems. B by m equal to gamma is something we have written for the present situation. Again, B, m and K, they are known values. They are parameters for this differential equation that are given to us. We are solving the equation given these parameters available. So gamma and omega naught square are known to us for a given system, and we have to find out x as a function of time. Anybody knows how to solve this equation? Characteristics, yes, very good. So what we do is we have to substitute e to the power of, so what we had done last time was we have substituted x is equal to e to the power of lambda t times a constant, right? Now in this case what happens is this won't work because we have a complex situation. So we write another equation for a variable y and we define a complex number z as a function of t as x as a function of t. Now x and y are both functions of time plus I times y as a function of t. I have defined that. I have defined the y equation as well. Y is this is called the companion equation. Okay. So now given these equations 1 and 2 and this definition of z, I can write z double dot plus gamma z dot plus omega naught squared z equal to 0. So that's a homogeneous ordinary differential equation in z, where z is a complex number. And what do I want to find? I want to find x. So all I want to find is the real part of z. So x, once I find z, as you will see, we'll find it by solving it. We'll want to find x ultimately, and x is nothing but the real part of my complex number, the complex function z as a function of time. So we'll be looking for the solutions to the equation number A now. So now we apply the ideas of the method of characteristics. So we say let's substitute z equal, now the dependence on time I'm not writing every time, it's taking space. So z by default means it's a function of time. A constant z naught times e to the power of, let's take it, alpha t. Right? So we'll make the substitution. Now when I say constant, that constant means it's not a function of time. It could be complex. Now we are working with complex numbers, so the z naught could be complex, except that it is not a function of time anymore. So this is not a function of time. This definitely is a function of time, as you can see that. And alpha can be real or imaginary, I don't know. We'll see what alpha comes out to be by solving the system. So let's substitute b in A. When you substitute b in A, that's what we get. This simplifies to the characteristic equation now. Right? Now this equation, we already know it's a quadratic, we can easily solve it. So alpha is minus gamma plus minus root the discriminant, which is gamma square minus 4 omega naught squared upon 2. This is the solution for alpha. So we have two roots here. So I can write my z, let's write it as a function of time this time. So z, which is ultimately what I want to find, I had started with a solution of the type z times e to the power of alpha t, right? Now I've got two roots. So that gives me two solutions. So one is e to the power of alpha 1t, let's call it z1 times e to the alpha 1t. The other solution I have is z2 e to the power of alpha 2t. Alpha 1 and alpha 2 are the two roots as seen from above. Now can I write a more general solution as a linear combination of these two? So z1 amount, I don't know what z1 is, that depends on the problem, I mean in terms of the integration constants. But can I say that some amount of e to the alpha 1t plus some amount of e to the alpha 2t? Is it allowed? If e to the alpha 1t is one solution and e to the alpha 2t is another solution, can I say that a linear combination of the two is also a solution of the equation? Can I always say that? Can I always say that for a differential equation, if I have two solutions, a linear combination of the two will also be a solution? How many people say yes? Please, can I see a raise of hands? How many people say a strong no? One, only one person is correct here. 2, 3, okay. We cannot do it every time. See, let's look at the equation. So let's say this is a solution and this is a solution, and this equation was a non-homogeneous equation. You substitute the first one, you get the right hand side. Substitute the second one, you get the same right hand side. So you get twice of that, or a linear combination of that. It only works if you have a homogeneous differential equation. That is, you have a 0 on the right hand side. If you do not have a 0 on the right hand side, superposition principle does not work if you have two solutions. Okay? Be careful there. Is that clear? It is homogeneous for this case, but my question was more general in the sense that in general is it true, because we tend to do that sometimes. Let's be careful about that. But for this case we can do it. So what's alpha 1? Now we have many cases, well at least 3 cases, but we will consider 2. So the first case is where this thing is imaginary. So case 1 is more commonly seen is where gamma square upon 4 minus omega naught square is less than 0. We don't know what gamma and omega naught are. Damping, if the damping was, let's say, very small, almost no damping, then that means that gamma, which is nothing but the damping coefficient B upon M, is very small. So it could be smaller than omega naught. So that means this, whatever is under the square root becomes negative. Okay, so this situation has a name, it has a tag, it's called underdamped. This situation is mostly you experience this kind of a situation where your damping is smaller than, well, gamma square is smaller than 4 omega naught squared, or gamma is smaller than, or we can write gamma is smaller than 2 omega naught, because remember gamma and omega naught both are positive values. D was positive, M was positive, and K was positive. So this we can say that gamma less than 2 omega naught is a situation where you have an underdamped situation. So we'll analyze this case first. In this case, our roots become, so alphas become, we'll try to take the I out, and this time we'll write a positive quantity inside the square root. So this is the alpha, and Whatever is under the square root, we will call it omega 1. Right? So let's write the solution now, the complete solution. Z as a function of time. Now this part, e to the power of, let's say alpha 1. So this part is real. So I can take that out because that's there in both roots. And in the brackets, then I can have a complex constant Z1 times e to the power of I omega 1 t plus another complex constant Z2 times e to the power of minus I omega 1 t. Now remember, Z1 is a complex number, e to the I omega 1 t is a complex number, Z2 is a complex number, well, a complex constant, and e to the minus I omega 1 t is a complex number, not a constant, a variable in terms of time. And e to the power of minus gamma by 2 times t is a real number. We can recall our complex numbers, right, from school? Did you study complex numbers as a part of your engineering mathematics course here? Not here, but back during JEE times you were good in complex numbers? Very good. What is I to the power of I? Square root minus 1 to the power of square root minus 1, what is that? You said you're good in complex numbers, tell me. Very good. Can we have a round of applause? Right. Okay. So e to the I pi by 2, e to the I theta is, so you know the polar form of the complex numbers. Okay. So that's how we write that. So we will use the idea. So e to the sorry, this was plus. Yeah, this was plus. So e to the I theta is cos theta plus I sin theta. That's called the Euler's form, the Euler's formula. Sorry. So we'll use that idea here. So when we do that, so we'll have Z1 written as, you can write Z1 as, let's say x1 plus I y1, and then you multiply that by cos omega 1 t plus I sin omega 1 t, and so on. So when you expand it, ultimately what you will get is a solution of the form, and remember we only want the real part. Okay. So you expand it, multiply the terms, you will get real plus I times imaginary. That is what you get ultimately in the complex number. And we want x, which is a real part of z, which in a general sense will come out to be that e to the minus gamma by 2 t will always be there, and then we have some constant. Now this constant is obtained by multiplying x1 with cos theta, and then you have y1 being multiplied by sin theta and so on. So many terms will be there. Ultimately you get c1 times cos omega 1 t and another constant times sin omega 1 t. Or we can also write that in the sense of, in the form of phase. So some constant times cos omega 1 t plus phi. So the solution of this equation of a damped harmonic oscillator for the case of underdamped situation where the damping coefficient gamma was small, this is what we get. So we see an oscillatory kind of behavior. Okay, so now that we have mathematically solved the system for a particular situation, we'll analyze the solution. Is this clear? Any questions till this point? Let's see what x as a function of time is. So x as a function of time has a periodic behavior, except unlike the last time or the last case where there was no damping, this time we have damping. So the amplitude of the periodic or the harmonic function is decaying with time. So if I was to plot it, something like this. And if we draw the envelope of the amplitudes, it will be something like, it's not drawn very well, but if you join the tips, you will see that it decays exponentially with time. Now, there are situations where gamma is actually much smaller than omega naught. Now, we're talking about a situation where gamma was less than 2 omega naught, okay, strictly. But there are situations where gamma is very small. So, if you want, you can write 2 omega naught, but that doesn't matter because it's very small. So, that means, or we can say gamma by omega naught is much less than 1. So, these are situations where you ideally do not want any damping. You want the system to sustain itself, but nature does not agree with that, so there will be some damping. So, you try to design the system in such a way so that the damping is very small. You reduce the friction, you put oil, whatever you want to do, you just try to keep this number very small. So, we have those situations where damping is undesirable, so we try to minimize it. So, this is that another special case out of that bigger case of underdamped. So, this is called lightly damped. On the other hand, situations where gamma by omega naught is not much less than 1. So, let us say gamma by omega naught or 2 omega naught is close to 1. Of course, in the direction where it is still less than 1. Happy? If it's much less than 1, really doesn't matter if you add a 2 there. Anyways, so yeah, so strictly it's 2 there, that's okay. So gamma by 2 omega naught is close to 1, still less than 1 but close to 1. So in that case, the situation is called heavily damped. If I was to plot a lightly damped case, it will seem as if there is no loss of amplitude, but it is slowly going down. Whereas if you draw a heavily damped case, okay, it dies very quickly. So that's the typical difference between lightly damped and heavily damped, but they are both underdamped situations. Is the nature of the solution clear? So now let's see some energy ideas. Yes, sir. Overdamped, have we talked about overdamped? We talked about underdamped. Overdamped is case 2 that I will talk about it later. Okay. Energy as a function of time is energy that we started with plus the work due to friction. Every time the system moves a small displacement, it loses energy because of the work done due to friction. So we start with some energy, and over the time energy will keep getting lost because of this non-conservative friction force. So energy at any given time can be written as this sum. Now earlier in the non-damped situation or the undamped situation, where there was no friction at all, there the energy was a constant. Right? We saw that it was half times Ka squared, but this time it won't be a constant. So let's see that. So let's find out energy as a function of time first. So this is the kinetic energy as a function of time plus potential energy as a function of time. Now what's kinetic energy? That's half times m times x dot squared, and potential energy is half times k times x squared. Now x, I've already given you this function. This is what x is, the solution. You can differentiate that with respect to time and get v. To save time, I will not do the mathematics here. I'll simply write the expression. So this is velocity. You differentiate displacement that we just found out as a solution. You differentiate that, you get this. Now remember, we will again talk about the situation of lightly damped situation. That was when your gamma by omega naught was much less than 1. So please allow me to write that without a 2. In that case, we also remember what this gamma was. Sorry, what omega 1 was. So this was omega 1. So for the situation where gamma by omega naught is much less than 1, you can easily see that omega naught is approximately equal to omega 1. Okay. Now what is omega naught? Omega naught was the natural frequency of the system when there was no damping. And what is omega 1? The frequency of the system when there is damping. So one thing we have noticed is when you have damping in a system, its resultant frequency also changes. Amplitude dies down with time. That is what we noticed for this particular case of under damped situation. But we also see that the frequency changes. But when the situation is lightly damped, that is your gamma is much smaller than omega naught, then you see that omega naught and omega 1 are actually almost the same. So whatever the natural frequency of the system was when there was no damping is approximately the same as the natural frequency when the system has got some damping. Okay. So you use these ideas, so you'll see that this is much smaller than 1. So this term, this whole term can be neglected. So velocity can be simplified as only the first part of the in the brackets. So our energy ultimately, when I add the two terms, comes out to be half Ka squared, that is what we had last time as well, multiplied by e to the power of minus gamma t, because gamma is small. Yeah, so this is for a lightly damped case. Okay, when gamma is much smaller than omega naught, and since omega naught and omega 1 are also approximately equal, so gamma is much smaller than omega 1 as well. So this is what the energy is. So this is what we wanted to find. How does energy change with time? It's very important. We would want to know that for a given system. So you start with some energy that was half Ka squared. So this is E naught, and the energy goes down with time. So if we plot this, it starts with E naught, then it decays asymptotically. Now we have seen this kind of a behavior in capacitors and AC circuits. So here our gamma, we need to find the time constant. The time constant is that time it takes to the energy to reduce by or reduce to 37, approximately 37%, e to the minus 1. So the time constant here is 1 upon gamma. So we call it damping time or time constant. That's typically how engineers will talk. The damping time of this system is this much. It's too much damping. Can we reduce the damping time? Oh, sorry, can we increase the damping time? That is, can we reduce gamma, or that is, can we reduce B, the viscosity? So we'll talk in terms of damping time mostly. Is that clear? Now I told you earlier that when we had talked about the time averaged values of U and K, we found out that they were the same for undamped oscillator. But that is not the case for damped oscillators. So I'll leave it to you, because you already know what U is as a function of time and what K is as a function of time. So please try to find out the time average values over one time period and see that they are not equal. Now, there is another word, that's another term that's used to find out the amount of damping in a system. It's called a quality factor of a system. It's called the Q factor. It's the ratio of energy stored in an oscillator at any time divided by the energy dissipated per radian, not per second, per radian, because we're talking about let's say different systems, so the cycle time will be different. So per second does not work when comparing two systems that have different frequencies, but when you do per radian, then you can compare, because one full cycle will be 2 pi radians. So in half a cycle, that will be pi radians for both cases. So we talk about energy dissipated per radian in this case. So Q factor is again used as a non-dimensional number to tell us whether, sorry, it's not a non-dimensional, so it's a dimensional number. So this is used to tell us whether there is, this is non-dimensional. So this is used to tell us whether the energy is, what is the damping situation of a system. So high Q factor means you have a lot of energy, or the damping is very small, the ratio of amount of energy you have and the rate at which you are losing it. And a low Q factor is just telling us it could be a situation where you do not have much energy, you are losing a decent amount of energy per time, or you have a lot of energy and you are losing a lot of energy per unit time. It basically gives us a sense of the ratio of the amount of energy it has and the rate at which it loses it. The high Q factors are good for situation where we do not want, where we want energy to be there, and low Q factors are good where we want to get rid of the energy quickly. So if you have a door, let's say it can open in both directions, right? You have seen those dampers used in doors. The spring as well. If there's no spring, the door will stay there. So the first thing you want to do is the door to close automatically. So what you do is you put a spring. So somebody opens it, leaves it, it goes, but it can open in both directions. Okay. So what happens is it keeps doing this, cut. It's very irritating. I mean, you want it to close quickly. So then you put a damper. That thing that you have, the piston, it's basically like a piston with some viscous liquid in it. So then when you open it, let's say it is an underdamped situation, so it does this, and then after a few cycles it stops. Okay. So in that case, would you want a high Q or a low Q? Low Q. You want the energy to be dissipated quickly. But actually we don't even want an underdamped situation. We want an overdamped situation that we'll talk sometime later, where there is no oscillatory system solution. It just does stop. Okay. Anyways, so this is the ratio of energy, and then dE by dt, well, it's a negative quantity, but we only take the magnitude, is energy per unit time, and we divide that by radians per second. So that gives us energy per unit radians, So this is what we have, and since energy we already know is this E naught times e to the minus gamma t. So when you substitute that in the numerator and denominator, this will give you approximately omega naught by gamma. I say approximately because it actually is omega 1 by gamma, but for this situation I'll say omega naught is approximately equal to omega 1 for this lightly damped situation. So this is our Q factor. The Q factor is a ratio of the frequency, angular frequency, and the damping constant gamma. So for a typical tuning fork that you use in lab, Q is approximately 1000. To give you some sense of numbers. In a tuning fork that you use for experiments, have you used that? Hit it and then it vibrates. Would you want a high Q factor or low Q factor? High Q factor. You want that fork to keep vibrating for a long time so that you can do your experiment. Good, good. Now the other case of an overdamped situation. This was all case 1 where gamma was less than 2 omega. So whatever was under the square root was negative. This is and we can see that this quantity now is greater than 1 because gamma square is greater than 4 omega naught square. So 4 omega naught square upon gamma squared is less than 1. So 1 minus less than 1 quantity is greater than 0. So we have a negative sign here, and we have, so this quantity is less than 1, this whole quantity is less than 1. So what we see is both roots are real firstly, and the second thing is both are negative, because if you have a negative sign in both of these, it's a negative thing, of course. If you have a positive sign in the second case, even then the quantity is less than gamma by 2, because whatever is in the square root after applying the square root, that's still less than 1. Okay. So we write the solution. Now this is all real. Well, Z is complex, of course, but we'll take the real part later. So Z1 and Z2 can be complex constants, but e to the power of alpha 1t and alpha 2t, they are both with a negative sign, they are both real quantities. Agreed? They are real roots. So x as a function of time if I wanted, I could have written e to the power of alpha 1t and e to the power of alpha 2t. But since I know they are both negative, so I take a mod of that and put a negative sign explicitly to tell you that this actually is decaying with time, and that makes sense. Should decay with time. X value should decay with time. Now this is not oscillatory. Unlike the case 1 that we had, if your damping is large enough so that it exceeds, so gamma exceeds 2 omega naught squared, you have a large damping, that's what you need in a door. You open it, it closes. It never hits, because you will see it's asymptotically decreasing to 0. It will never hit. But if you have a door opening on both sides and you have an underdamped situation, it will do this. Or if you do not allow, if you have a strict stopper, then it will do tuck, it will hit, it will want to go the other way around. But if you have a heavily damped situation, if you have an over damped situation, in that case, it will never touch the other end. Smoothly close. That is what, there is a tuning in the damping system, you can increase and decrease it. So when you buy it and install it, you can increase it. Sometimes the setting goes bad, the liquid leaks, and sometimes, then you will see that these doors will suddenly start hitting. So then it's time to some servicing on the damper, not change it, I mean you can do some servicing and get it working so that it is again heavily damped system. So there is all physics here. Okay. So this this brings us to the end of the first part of this oscillators that were damped oscillators. Now remember that I told you that these oscillators are, we are talking about a simple system where you have a spring and mass system with a damper. But in real life, there are many situations in engineering which can be modeled using this kind of a spring damper system. It may not have, there may not be a physical spring or a damper, but the mathematical equation will come out to be of a second order ordinary differential equation which has terms this one. You might have an equation which looks like this for a system that is complete, that has no analogy with this physically, but mathematically you have the same equation. So what you will see is whatever you have learned here, those ideas will be applicable. So you'll have situations where it will show an oscillatory behavior, you'll have a situation where it will show a non-oscillatory behavior, you'll have lightly damped situation, heavily damped situation, and all these ideas of Q factor and so on can be talked about in those situations as well. Now the second part of this discussion is when you have forcing. Now let's say damping is there's nothing we can do about it, that's reality, let's live with it. But what we can do is we can apply a force constantly so that we can compensate for that damping. How will we do that? How will we mathematically analyze situations where you have forced oscillators? Now again in forced oscillators, there is a new term coming because of forcing. So we will talk in two parts. The first one is when there is no damping but we are forcing it, and the other case is there is damping and we are forcing it, just to make the mathematics tractable. The first part is quite straightforward, the second one will require some more mathematics. So first part we'll try to finish off today, and the second part we'll take it to the next lecture. Undamped forced oscillator. So we have a spring mass system, but in this case we are applying a force to the mass, and this is a function of time. There is no friction, there is no damping in this case. And force is a function of time, so how do we proceed? We'll have to start with some nature of this oscillatory force, so of this transient force. So we'll call it an oscillatory force, harmonic force, which is F naught cos omega t. F naught is a constant, and omega is the frequency of forcing. Now this omega is not the same as omega naught or omega 1 that we have talked about. It is some omega. You can change it. Let's say you are applying a force with your hand, so you can change what frequency you apply in this case. So this is forcing frequency, and F naught is just a constant. So if we write the model equation, we get mass times the acceleration is restoring force plus F naught cos omega t What is the major difference between this equation and what we had in the past, previously? This is non-homogeneous, and I'm sure we know how to solve non-homogeneous ODEs, the general solution and the particular solution. You know that. If you don't know it, then I have no time to discuss that. But what we, the solution, general solution, x is the function of time for this case, is the solution to the homogeneous equation. Now, homogeneous equation is when you make it 0. That we already know. That was the undamped spring mass system. So, what was the solution there? Can we chat outside the class, please? So, this is the solution to the homogeneous equation. It has two constants of integration, but that is not the complete solution here. This is only the homogeneous equation. I mean, if you put it in this, if you substitute this, it won't satisfy the equation. All it will do is it will make the left hand side 0. You have to add something to it, which is a solution of the non-homogeneous, a particular solution, not a general one, and that is something we can find by test. So, this is, we'll call it the XP, the particular solution. If you do not remember this, you can go back to your engineering mathematics and you will be able to see that in the book. The idea is that the first part satisfies only the left hand side, so it is not a solution of the equation number A, but if we add any one solution to the whole equation, not a general one, a particular one, which has no constants of integration, if I substitute that, then the solution becomes a general solution of the whole equation. Okay, the second part, the particular solution, has to be found out using different techniques. The easiest one for us is, now we are forcing it with a frequency which is omega, cos omega t. Let's try to see if the solution A, some constant A times cos omega t is a solution of this equation or not. You will see it is a solution. Okay? So, if you substitute this A cos omega t into the equation number A, x equal to A cos omega t, that will give you a solution. Well, that will tell you it's a solution with A being equal to, so if you substitute x equal to A cos omega t in A to find, well, xp, to find the constant A. That gives us x particular, so the constant A becomes, well, again I am not doing that, you can do it by yourself, it is not very difficult. So, this is our particular solution. So, the overall solution is this. This is the mathematical solution to the equation of an undamped forced oscillator where the forcing is f naught cos omega t. So, we will want to analyze this solution now and understand the behavior of the system. Now, see what happens is, now this is undamped, but if you had a damped system, this B will be a function of time. I am telling you a general behavior. So, if the system was damped, your B would be a function of time, like you had A as a function of time earlier. So, what happens is it decays. So, the effect of the first part ultimately dies down. What remains is this part. Unlike the previous case when there was no force, if there was no force, the system, if you take the door and leave it for an underdamped situation, it will oscillate and ultimately stop. But this will not stop. This will keep oscillating because you keep on forcing it. So, the part that comes from the last case, the homogeneous case, where it was oscillating and stopping after some time, that effect will be dying down. Okay. Only the second part remains. frequency will be changing. Yes, I mean omega is different from omega naught. Well, let us say for this case we are forcing it with a constant frequency omega. We can change it. That is, see, we cannot change omega naught. Omega naught is a function of the system, but omega is in our control. So I am forcing it with a particular frequency omega. Okay, so the steady state behavior of the system is not dependent on initial conditions. It is only dependent on the forcing. The steady state solution for the previous case was 0. For this case, it is the second part, term 2. Do we have a class after this? No? So let's see only term 2. So term 2 is oscillatory. It has a frequency equal to frequency of forcing. What about the amplitude? If my omega was 0, so let's say omega on the x-axis, if omega is 0, what happens? You have a positive amplitude, some value, let's say this value, and when I increase the frequency, does amplitude increase or decrease? It increases because the denominator omega naught squared minus omega squared is getting smaller and smaller, and what happens at omega naught? It goes to infinity, and when you increase it further, let's say you are coming from the other side, then it's negative. This is the amplitude. Okay. What happens at omega naught? Resonance. Resonance happens at omega naught. The resonance happens when the forcing frequency becomes equal to the natural frequency of the system. Is resonance desirable? That depends. On a bridge, is it desirable? When can you think of a situation where it is desirable? Musical systems, yes. Organ pipes, harmonic, flutes and so on, you want resonance to happen so that you can get sound. Well, electric oscillators, earlier used to have those radios where you tune in, so those oscillation, again electrical oscillations, we wanted resonance so that it tunes into the channel. So what we are seeing is that for this forcing, we have to be careful whether we need resonance or we do not need resonance. Now we are out of time. I had a demo for you where I would have shown you these things physically, but we'll do it in the next class when we talk about these systems, and then we'll move to the damped forced oscillators. Thank you. So I'll see you on Wednesday.